In this video, we are looking at the data collection for lab number 1, looking at refraction. So when you first go to the simulation website, you're presented with these choices, and we just want to click on the intro. And that is going to bring us to this menu here. So we have our upper medium in white, and then we have the lower medium in sort of a grayish blue. And in these two menus over here, we can choose what we want for the upper and the lower medium. So I'm just going to leave the upper medium as air, and I'm going to change the lower one to mystery A, because this is one of the materials whose index of refraction we are going to measure. Now this is the laser over here. You want to click the little button to turn it on. So click once, and now we see the red laser beam. So this one here is our incident beam. This one down here is the refracted beam. And the simulation also shows the reflected beam over here. We won't be needing that for anything, so just don't worry about that one. You want to leave the laser as a ray and not as a wave. And then we have our protractor tool over here. So you can click and drag to bring this over to the medium. Now, when looking at refraction, all of your angles are measured relative to the normal line. So that's this dotted line here, which is perpendicular to the surface. So you want to line up your protractor with that normal line, so that you can correctly measure your angles. And you can choose any incident angle you want. If you want to reposition the laser, notice that when you hover the mouse over top of the laser, these little green arrows come up. That allows you to change the incident angle. And you can see that the refracted and reflected angles also change. So just for convenience sake, I'm going to set my incident angle to 60 degrees. You can use any angle you like. It shouldn't make a difference. And then I can read my refracted angle off of the protractor down here. Now, just because this is a simulation doesn't mean there's not uncertainty associated with these measurements. So we have our protractor here, which is similar to a ruler with millimeter divisions. So in this case, our protractor has very small divisions of 1 degree. So that means you need to consider the reading uncertainty of the divisions on your protractor. The other thing you'll want to consider is the fact that the laser beam itself is a little bit wide. So you'll also want to consider that as part of the reading uncertainty. So when we have these very small divisions, typically you would use half of the smallest division. And then you'd also want to consider maybe using about half of the width of the beam as part of your uncertainty. So once you've looked at your incident angle and measured it on the protractor, then you can also measure your refracted angle. So that's the angle, again, from the normal into mystery medium A. And you're going to record your measurements for the incident and the refracted angle, as well as the index of refraction of the upper medium. Now, these indices of refraction that are given, we can consider those to have uncertainty of 0. So the index of refraction for air is 1.00, plus or minus 0 uncertainty. And when you're ready to make your next measurement, you want to select the next option. So we want to switch it over to water. And you can even leave the incident angle the same. There's no need to change it. And all you have to do is make a new measurement of the refracted angle as well as including an uncertainty on that measurement. And you also want to record the index of refraction of water, so that would be 1.33. Again, you can use a 0 uncertainty for the index of refraction value. And then finally, you want to use glass as the upper medium. Again, you can leave the incident angle the same, and you just want to record the new refracted angle down here, and also record the index of refraction. So that would be 1.50, and again, there would be 0 uncertainty on that measurement. Once you've collected all of your data for mystery material A, then you're going to repeat the process using mystery material B. So we'll go back to air, and the lower medium is mystery B. So now I'm going to talk about how to appropriately use the Excel template that I've shared on the Moodle course page for lab number 1. When you first download the spreadsheet, you're going to have a lot of empty things that you need to fill in. One of the first things you'll want to do is fill in your name, your student number, and the date. I would also recommend renaming the file to include your name somewhere in the file name so that I know who it belongs to when you submit it. Then you'll want to fill in your data. There is a spot for mystery A, so if you kept the angle of incidence constant, you can fill that in here. And then you can fill in your measurements for the angle of refraction, as well as the N1, so the index of refraction for air, water, and glass. Then if you scroll over to the side, there is another area to enter your data for mystery B. Then if you scroll down, there is a setup area to fill in your Excel equations so that you can do your calculations. And then below that, there is another data section for the second part where you're doing total internal reflection and calculating the index of refraction there. So I'm going to switch over to my Excel spreadsheet where I've already filled in my data now. And you'll notice in the calculations, the first thing I've done is placed an area for you to convert your angles into radians. There are 2 reasons you want to do this. Number 1, Excel can only use trigonometric functions when the angle is in radians. So if you try to take the sine of an angle in degrees, you'll just get a nonsense result. And although it is possible to nest the functions together, I like to put the radian calculation separately as a reminder that that needs to be done. The other reason why we need to do this is that anytime you have a measurement and that measurement has an uncertainty and it's an angle, then that angle uncertainty also has to be in radians when you're using the uncertainty propagation formula. So not only do we need it for our Excel formulas, but we also need it for our uncertainty propagation. Luckily, Excel has a built-in function to convert from degrees to radians. So recall when you want to do a calculation in Excel, you always have to start with the equal sign. And the special function is just the word radians. And you'll notice when I start typing, Excel will try to guess what function I want. So I'm going to click this function and, oh, didn't mean to do that. I'm going to click this function, and then I want to convert my angle of incidence into radians, so I'm going to close the bracket. And I also want to do the same thing to my uncertainty, so I can just drag the formula to the right, And it also converts my uncertainty into radians. And then I also want to add in my percent uncertainty calculation. So these were pre-formatted to show percentages. Now I want to do the same thing for my angle of refraction. So I'm going to start typing radians, and I want to pick my theta 2 up here, close the bracket, and I can drag the formula to the right. That's going to convert my uncertainty. And now I can also drag the formula down, and I've done all of my conversions to radians very quickly using the Excel built-in function. And I'm going to add in my percent uncertainty here and drag this down as well. Now, once I've rearranged equation number 1 to figure out the index of refraction for N2, so that is the lower medium, in this case it's mystery medium A, then that's going to be equal to N1 times sine theta 1 divided by sine theta 2. So I'm going to start with an equal sign and going to use the cell where N1 is stored, so that's up here, multiply by sine of theta 1 in radians, so that's this value here. Now, because I kept my incident angle the same, but I want to use the dragging function in my Excel, then I'm just going to put a $sign here, and that is going to keep that value constant. Then I want to divide by the sine of theta 2, also in radians, and close my brackets. And now I can take the corner, drag it down to calculate the index of refraction for the mystery medium A when the upper medium was air, water, and glass. Now, before I talk about the uncertainty, I'm going to switch off of Excel and go to a piece of paper so I can talk a little bit more about using using calculus to propagate the uncertainties. All right, so now we are going to look at how to use calculus to propagate the uncertainty when we're using equation number 1 to find the index of refraction for our mystery medium. So that will be our N2. So first, I'm going to write down the equation solve for N2. So we have N2 is equal to N1 sine theta 1 divided by sine of theta 2. And if I take the general rule for uncertainty propagation using calculus, then first of all, I see that there are 3 variables that N2 depends on. So it depends on N1, theta 1, and theta 2. So my delta N2 is going to have this form. So I'll have partial derivative of N2 with respect to the first variable, so that's N1, that's all squared, and then that's times the uncertainty of N1 squared, plus partial derivative of N2 with respect to the next variable, so that is theta 1 squared times uncertainty of theta 1 squared, plus the partial derivative of N2 with respect to the third variable, so that is theta 2 squared times uncertainty of theta 2 squared, and then that whole thing is square rooted. Luckily for us, in our experiment, all of the index of refraction for N1, they all have an uncertainty of 0. So we can cancel out this first term right away. And our values of uncertainty of theta 1 and uncertainty of theta 2, those were from your measurements. And it is important that you use these angles in radians. So the only thing we're missing are these two partial derivatives. So I'm going to do that work down here. Now, first partial derivative that I need is N2 with respect to theta 1. And that means that I'm taking the derivative of this whole expression where theta 1 is a variable, and then N1 and theta 2 are considered constants. So I'll write it like this. Now, because N1 and theta 2 are constants, I'm just going to pull those out in front. And now I have N1 divided by sine of theta 2. And now I'm just taking the partial derivative of sine theta 1 with respect to theta 1. And using reference tables, the derivative of sine is positive cosine. So that gives me a final result here of N1 divided by sine of theta 2 times cosine of theta 1. So this expression is what goes into these brackets up here. Now I just have to do my second partial derivative. Now this one's going to be a little bit more tricky. You'll see why in a minute. So we have partial derivative of N2 with respect to theta 2. So in this case, now theta 1 and N1 are constants. So I'm going to write N1 and sine of theta 1 out in front. And I have partial derivative with respect to theta 2 of 1 divided by sine of theta 2. So we have a few things happening. We have 1 over and we have a sine function. So that means we'll have to apply the chain rule for taking our derivatives. I'm just going to rewrite it first as N1 sine theta 1 and then partial derivative here. And I've got sine theta 2 to the power of minus 1. So note this to the power of minus 1 means that it's 1 over, not that it is the inverse sine function, because those will give you two very different things. So using my chain rule, I'm going to keep my constant out front here again. So first, if I take the derivative of the outside, I have negative 1 times sine of theta 2 to the power of negative 2. And then that's going to be multiplied by the derivative of the inside. So remember from before, derivative of sine is cosine. So that gives me cos of theta 2. And then close all that brackets. And so now simplifying and putting this all together, I end up with negative N1 sine theta 1 cos theta 2 divided by sine of theta 2 squared. So it's a little bit more complicated, but we can work it out using what we know about calculus. And then this expression goes into these brackets up here. So I find it easier to work out these individual parts, which you'll see when I go back to the Excel spreadsheet, so that you don't have a big giant expression in your Excel spreadsheet. So we just looked at how to use calculus to determine the uncertainty propagation formula for the index of refraction of N2 for the mystery medium. And that resulted in quite a lot of trigonometric functions being used. So to break things down a little bit, I put in a little section underneath for the uncertainty propagation. So that's where we can figure out the numerical value for the partial derivative of N2 with respect to theta 1, and then the partial derivative of N2 with respect to theta 2. Now, I won't always work all these out ahead of time, but since this is the first experiment where you're using calculus to propagate the uncertainty, I'm going to go ahead and give you a little extra help here. So we've already worked this out, and we know that this partial derivative is equal to n1, so that value was stored up here, times the cosine of theta 1, so cos theta 1, making sure I'm using the radians value, and then that was divided by the sine of theta 2, which is here, again, using the value in radians. And I want to be able to drag this formula down, so I just want to add in my dollar sign here. That's going to keep the cell constant for theta 1, but allow the other values to increment when I drag my formula down. So now I've calculated the 3 partial derivatives that I need here, and I'm going to now calculate my partial derivative of n2 with respect to theta 2. Now, if you remember, this one was a little bit more complicated, so we had negative 1 times n1, that was up here, times sine of theta 1 in radians over here, times cosine of theta 2, also in radians over here. And I want to close that bracket, and then that was divided by the sine of theta 2, which is also here. Again, oopsie, what just happened? Exited out. Okay, back to it. We have sine of theta 2 in radians, which is right here, and then that one was all squared. So this is only going to square this sine function because Excel will follow the rule for order of operations. So I don't have to worry about putting in any extra brackets there. Now, again, I want to be able to drag this formula down. So before I do that, I just want to add in my dollar sign for my theta 1 because I want to keep that one constant while I increment the other values. And drag this down here. So now I've done sort of the hard work over here, and now I'm ready to type in my formula for the uncertainty for my index of refraction for N2. So this is equal to the square root, so using the square root function sqrt, and it's the square root of this first partial derivative squared times the uncertainty of theta 1 squared using the value in radians. So that's this value here. That's going to be squared plus the second partial derivative squared times the second theta uncertainty in radians, also squared. And then once again, I want to be able to drag this function down, but my theta 1 value, or sorry, the uncertainty of my theta 1 value is not going to be changing, so I'm going to throw in that dollar sign to keep that value from incrementing. And if I take the corner here and drag this down, that has given me my uncertainty calculations for all 3 measurements. And finally, because we measured the index of refraction for A using 3 different upper mediums, but we expect to get the same result for all 3, it makes sense to average our three values. So I can use the built-in averaging function. It's just the word average, and click and highlight the three values I want to average. And remember that the uncertainty of an average is related to the standard deviation of the values you're averaging. And that is equal to 2 times the standard deviation, and we want to choose the standard deviation S of the values, not the uncertainties. And then that's going to be divided by the square root of however many values you're averaging, which is 3 in this case. Now, recall that when you are stating your final result, the final uncertainty of an average value, you have to choose the larger of the two uncertainties when you're looking at either the calculated uncertainty of the average or the individual uncertainties. So basically you're looking at these three values here and this value and picking out which one was the largest when you are stating your final result. So because this is a smaller number, that just means that these values were all close together. So we have to use the larger number when we're writing our final answer. And of course, you can fill in the percent uncertainties again here. And then once you've finished your calculations for mystery A, you can head on over to mystery B, and you can repeat the same calculations. In the second part of our experiment, we want to use something called total internal reflection and the measurement of the critical angle to do a calculation for our index of refraction of both mystery A and mystery B. Now, what we want to do is we want to set our laser so that it is basically just skimming the surface of the two mediums. So we want it to be almost at a 90-degree angle to the normal here. So you want to drag this laser down as far as you can go before the refracted beam disappears. So at this point, I'm perfectly level and the refracted beam has disappeared. So I want to go back up just at the tiniest little bit. And now I can see a refracted beam inside mystery medium A. So this angle is going to be the measurement of the critical angle. And this is what you'll need to measure in order to use equation number 2 to calculate the index of refraction. Now, equation number 2 is only valid for when the upper medium is air. So make sure that you do have air selected over here. And that also means that you're just making one measurement. You're not doing multiple trials or using different materials when doing the measurement for total internal reflection. But we still want to measure mystery B. So once you've measured your critical angle, so from the normal line to the refracted beam, then you just want to switch over to mystery B on the bottom here. And again, this is going to give the critical angle, so you want to measure the angle from the normal to the refracted beam. And using this measurement, you'll be able to calculate the index of refraction using equation number 2, where the upper medium is air, and the angle you're measuring here is that critical angle. When you've collected your data for the critical angles, then you want to go ahead and fill them in. First of all, you're going to record them in your notebook. And then once you've recorded your data, you want to fill them in on the Excel spreadsheet. I went ahead and filled in my value here already. And this is a shorter calculation because we only did one measurement, so we're only going to have one calculation to do. And we want to do the same thing that we did in the first part, which is convert our angles to radians. Remember that Excel can only process trigonometric functions when the angle is in radians, as well as our uncertainty propagation only works when our uncertainty is in radians. So using the function that converts degrees into radians, I will select where I had my value stored. And I also want to convert the uncertainty, so I'm just going to drag that over and then fill in my percent uncertainty, so uncertainty divided by the value. And I want to use equation number 2 to calculate the index of refraction here. So if I rearrange equation number 2, I end up with have to start with an equal sign, 1 divided by the sine of the critical angle. So remember, I need to take the sine of the angle in radians, so I'm going to do that here. And in order to calculate the uncertainty, once again, I have to use my uncertainty propagation method using calculus. So one more time, I'm just going to switch over to a piece of paper, and then we will finish up with Excel. So we have equation number 2 here, and if I rearrange this equation to solve for n, I have n is equal to 1 divided by sine theta c, where that is the critical angle. And I could also write this as sine theta c to the power of -1. Again, this is 1 divided by sine, not the inverse sine function. They're two very different things. Now, in this case, n only depends on one variable, so our uncertainty propagation will be a little bit easier this time. So writing out the general form using calculus, I have delta n is equal to partial derivative of n with respect to my variable. My only variable is theta c. That's squared, and then multiplied by the uncertainty of theta c squared, and that is all square rooted. There's no more terms here, so I can make my life a little easier, and I can cancel out the square root and the squares here. So that just gives me absolute value of this partial derivative times the uncertainty of theta c. Now, all I have to do is figure out what goes here, because my uncertainty came from the measured value. So when I want to take this derivative, I have the partial derivative of my n, which is sine of theta c to the power of -1 with respect to theta c. Now, since there's only one variable here, we can basically just treat this like a regular derivative. And all I have to do is apply the chain rule, just like I did in the previous uncertainty propagation, and I'll have my expression for my partial derivative. So I have derivative of the outside, so I have -1 times sine theta c to the power of -2 times the derivative of the inside, which is cos of theta c. And then that gives me a result of negative cos theta c divided by sine theta c squared. And I can put this back up into my expression here. So I end up with my delta n is equal to absolute value, negative cos theta c divided by sine theta c squared times delta theta c. All right, now that we have worked out our uncertainty propagation formula for N2 using total internal reflection, we can type this into Excel to calculate our numerical value. So we had an absolute value and a negative sign, and again, to make my life easier, I'm just going to take the absolute value before I plug it in, meaning I'm just going to drop that negative sign. So I have cos of theta c, and theta c in radians is over here, times the uncertainty of theta c, which again has to be in radians, and then that is divided by the sine of theta c in radians, and then that sine function is squared. And now I've calculated my uncertainty for N2, where it is mystery A. And once you are looking at your final results, you'll notice that in the measurements using the law of refraction, we calculated N2, and using total internal reflection, we also calculated N2 for the same material, meaning that you'll want to compare the values that you got from the two different methods to see if those values agree with each other within uncertainty. And hint, because it was the same material in both cases, you would expect those values to agree in both internal reflection, total internal reflection, and law of refraction. And then again, you just want to repeat those same calculations once you've made your measurements for mystery B, and make that same comparison from the two different methods. So not comparing B to A, but comparing B from the two different methods, because it's still the same material, so you would expect to get the same index of refraction no matter what method you use to calculate it.